Okay, so this should be our last lecture on this module. So we're going to be looking at exponential growth and decay models. They also follow a model much like continuously compounded interest. The textbook writes the formula this way. So this y of naught will be the starting amount. Y will be the amount that you get after time t has passed, and t can be any block of time. So when we were looking at interest problems, the block of time was in years. Here it could be hours if you're measuring bacteria growth, months if it's a colony of rabbits or wolves, etc. So most of the time when we're thinking about exponential growth and decay, y is actually a function of t. The same thing in continuously compounded interest. The capital A is a function of t, but it's most commonly just written as a. But we might want to write this as a function of t. So that's not y times t, that's y as a function of t. K is going to be the rate, either a growth rate or decay rate given as a percentage. But just like we did with interest problems, that percentage must be represented in, K in this case must be represented in decimal form. So with continuously compounded interest, the rate in decimal form was R. Here it's a K. You have to be very careful. K will be positive if we're referring to growth. So we never had to worry with interest rate problems because your money was put into an account and your money grew. K will be negative if we're talking about a decay problem, if something is decaying over time. And of course T is any amount of time. So T can be seconds, years, months, what have you. Okay, so for example, rabbit populations obey the exponential growth equation. Okay. So this is a typical problem. If 200 rabbits are released on an uninhabited island and the growth rate is 3.5% and time is taken over months, approximately how long will it take the population to double? So how many months will it take this to double? Okay, so what we can fill in here is we want to find t, how long until the amount after time t is double what you started with. Okay, so this is going to be, this formula will become 400 is equal to what you started with times e to the power of k. Now this is a growth rate, so that will be positive 0.035, so 3.5 divided by 100, and then t. And we have to find t. We cannot do a conversion formula yet to logarithmic form because I have to have something to a power by itself without anything in front of it. So I just divide both sides by 200. And now it's just a straight conversion. That's going to be my A. That's going to be my Y. Trying to get a color that shows up better. No, that's all I have for now. That's going to be my X. And so in my red, I'm going to get that. And so I'll have the logarithm of the red A, which is E, taken at the red X, is equal to that. And so ln of 2 is equal to that. I need to find the time, and the time here is in months. And so that's going to be my answer, and so that's what I put into the calculator, ln of 2 divided by 0.035. So about 20 months if I take it to the nearest month. So about 20 months. Okay, so notice that we didn't even actually have to know the beginning amount to solve that. Suppose all we knew was that the growth rate was 3.5%, and the question was how long would it take the population to double? Well, I would replace k with that. And if the starting amount is y of naught, you want to find t, how long, when the amount after time t is double the starting amount. And so I would have done this, and then I could have just canceled those or divided those on each side, and I would have gotten the same formula there, and I could have done the conversion rate. One of the easiest questions on this would be how long until the population reaches 300? If I have this information. So we start out with 200 rabbits, and the growth rate is 3.5%, so k is 0.035. So how long means you're solving for t. Okay. Until there's 300 rabbits. Well, I want to find out the amount of time it takes for there to be 300 rabbits. And then again, I would just divide both sides by 200 and then do a conversion. Another question is, how many rabbits after 3 months? Well, that's your t. And so if we start with 200 and the growth rate is 3.5%, then I just solve this for y of 3. And that is the easiest of all to do. I just put that straight into my calculator. So I do 200, then times second ln e to the power of 0.035 times 3, close parentheses. So about 222. Okay, so I hope we're seeing the similarity to continuously compounded interest problems. All right, now what if we have a decaying substance and we're asked something about the half-life? What is half-life? Half-life is the amount of time required for half the amount of the substance to decay away if you have a deteriorating substance. So suppose a substance has a half-life of 4 days. Some people wrongly think that if it has a half-life of 4 days, then in 8 days it's completely gone. That's not how it works. Here's how it works. If it has a half-life of 4 days, then suppose this is what you start with, what's shaded. So 4 days from now, half of this will be left. So you've got what's shaded here. Then in an additional 4 days, you'll have half of what you had here. So that's what you have in additional 4 days. And 4 days hence, you'll have half of this, and so on. And that's how it works. And so you can see it will take a lot longer than 8 days for all of that to be gone. That's how half-life works. So suppose a radioactive substance has a decay rate of 2.1% measured in years. Approximately how long is the half-life? So how long, and the time is in years. So how many years will it take for half of that to decay away? All right, well, what do we know? We've been told we have a decay rate of 2.1%. So K, since it's a decay rate, is going to be negative. And that has to be a decimal. So 2.1 divided by 100, 0.021. So my formula becomes this. Now, how long means we want to find T when the amount after time t is half of what we started with. So we want to find t when y of t is equal to 1/2 times what we started with. Okay, well, you put these equal to each other because that's y of t and that's y of t, so put them equal to each other. And we can see now again the y naughts cancel. You can divide both sides by y of naught because we know what you start with is not going to be 0. And again, what do I do now? I can do a conversion. I'm trying to find my red pen. Let's see. So I've got a to the y equals x, and I want to write that in logarithmic form. So I'm going to have the logarithm of base e of 1/2 is equal to the red y. And I want to solve this for t. And so the logarithm of base e is just ln is equal to that. And to solve for t now, well, I have negative 0.021 times t, so divide both sides by negative 0.021. Those will cancel, and that will give me how many years it will take to get half the amount. That will be the half-life. So ln of 1/2, you can do 0.5 if you want, divided by negative 0.021. So about 33 years. Okay. Let's see if we have time for one more. Okay, suppose an experiment begins with 12 grams of a radioactive substance where the decay rate is measured over days and is 6.5%. How long until only 3 grams of the substance remains? So again, you're going to have to solve that thing for t for time. Okay, so let's start out with our formula. Okay, so how much did we start with? We started with 12 grams. This is a substance that is decaying away, so my K is going to be negative, and 6.5 divided by 100, so my K is going to be negative 0.065. And what do we want? We want how long, so find t, when the amount after time t is equal to 3 grams. Well, both of these equal y of t, so you put them equal to each other. So we want to solve this for t. So before I can do a conversion, or I could take logarithms of both sides. That's also another way you could do it. I need to get rid of the 12. Okay, so that... I like to work in decimals if they're nice, only if they're nice, and that's nice, so 0.25. Now, we could do the conversion. There's a to the y and x, and you can do a conversion, and I've done that numerous times. Another thing you could do is take logarithms of both sides. Well, what base do you use? Well, what's the base here in that exponent? The base is e, so take base e of both sides. So this is another way that can do it. Doesn't matter which way you want to do it. Now, if I use Rule 3, what does Rule 3 say? You can take something that's in the exponent and it comes out the front. So now, why did I choose natural logarithm? Because this is that. And when that's the same, you just get 1. So that's the number 1. And then now I can divide both sides by negative 0.065. And so this is my t. And t is going to be ln of 0.25 divided by negative 0.065. So it will be approximately, it's in days, so it's going to be, excuse me, approximately 21 days, or 21.3. They'll tell you on the test how much to round it to. Okay, so like I said, if you wanted to do the conversion, so you can either take logarithms of both sides. I'm choosing to take base e because I want that nice cancellation there. Or I could have done the conversion. A to the y is equal to x. And then go back to the original black and you get this formula. Either way is fine. That concludes the last lecture for this module. Hooray!